Good afternoon, everybody. I'm very pleased to introduce today's speaker at our virtual pub. So today's speaker at our pub seminar is Marcello Alecci from the University of L'Aquila. L'Aquila is a town in center Italy. Marcello is a physicist and is well known in the community of magnetic resonance. He studied physics in Rome and then he got his PhD in biomedical physics and bioengineering from the University of Aberdeen, Scotland. Then I would say that the main scientific interest of Marcello is the physical understanding and technological advancement of electron and nuclear magnetic resonance imaging, and this application in biology and medicine. So this is, as you know, quite an important area in which these modalities are still developing. And I think that what is that from the title of Marcello talk today, I think we will learn something new concerning the possibility to increase the sensitivity of detection in the magnetic resonance phenomenon. This actually is the major drawback for this spectroscopy, and that could really be further developed once that the problem of the sensitivity in the detection will be, let's say, will be improved. So today Marcello will talk us about metamaterials and magnetic resonance, theory and application. So Marcello, the floor is yours.
Good afternoon to everybody. Thank you for the nice, kind presentation, Silvio. And I would like to thank the Euro-BioImaging Consortium for inviting me to talk today, and Silvio, Aime, and Professor Bifone for the personal invitation. As far as I know, Euro-BioImaging aims in spreading innovation in imaging technologies and has established a workflow to ensure new technologies are continuously integrated into the community. And today, my talk is aimed to this goal with respect to the specialistic topic of metamaterials in NMR, MRI in general. In my talk, I will give a general introduction, and in the last part, show our latest technology developments on this topic at our university in L'Aquila. So the outlook of my presentation is shown here. Since many of you do not know our group in L'Aquila, I would like just to show who we are and what we do very quickly, and then review the hardware that is currently used in spectroscopy and imaging with magnetic resonance, and going towards the current trends that, in my opinion, are most important at the moment with respect to hardware development. And to this aim, I will talk about metamaterial science that is meeting magnetic resonance, and then show our current development in L'Aquila. So we are a small university at the middle of Italy, 100 kilometers from Rome. This is our small research groups that comprises physicists, engineers, and biologists by background. And The lab was founded by Professor Soggio in 1982, and our expertise is, I would say, on magnetic resonance technology, physics, but with applications to medicine. And from the experimental point of view, our lab is equipped with electron spin resonance, and then we have some scanners for small animal imaging at 1 Tesla at 2.35 Tesla. We are also working on ultra low field NMR and MRI. We do also in vivo work with animal models of disease, and we are also engaged in technology development and school on NMR and MRI. We have a number of international and national collaborations shown here, and we are quite involved with the Italian discussion group on magnetic resonance, and we have organized in the past years a workshop on hardware and the national meeting in 2019 in L'Aquila. We are also busy with schools on RF coil design, which is one of the most advanced topic I believe we work with since the past 20 years. And we were very happy to be able to organize in 16, 17, 18, 3 international schools with the support of the European Society of Magnetic Resonance in Medicine and Biology. And the topic was the actual design and testing of RF coils. And as you can see here, we had an especially equipped lab where our students, PhD students coming from everywhere in the world could build their own coil. We are hoping to be able to organize next year again the school if the COVID condition will allow. We are keen to develop new methods and technology, and over the past years we have filed and have received 14 patents. And the last patent, the Italian and the PCT patent we are working at the moment is the subject of the talk today about metamaterials. But just to give you a glimpse of what we do in terms of innovation, this might be quite interesting for some of you. My colleague Angelo Galante is working actively on a monitoring method for personal exposure to static or quasi-static magnetic fields. This is related to safety in NMR, MRI, and is of very broad general use. And Angelo is quite keen to looking for collaborations. We are also working on characterization of hydrogels with magnetic resonance imaging, and of course on metamaterial as we are talking today. Since I know some of you are not working every day with spectroscopy and imaging with magnetic resonance, I am going to show you a short review of how it's made, the hardware, and what are, in my opinion, the current trends to this respect. A magnetic resonance detects the signal of water in tissue. And it is also able to detect the signal from other nuclei like sodium, phosphorus, and so on. And the nice point of magnetic resonance spectroscopy and imaging is the ability to combine the anatomical, the structural information with also spectroscopy information, like it's shown here in this example. So a nice image, and from a given voxel we can get spectral information that are providing physiological or pathological information. at the moment, this technique is spanning from magnetic field that start from micro Tesla and end up to 30 Tesla. So a very broad range of magnetic field, which means a very broad range of technology and methods that need to be developed to optimize the specific application. So there is lots of research going on. If you look at the main components of the hardware used in our scanner, of course, you start with the human body or the sample you are studying, which is providing the useful nuclei that we are going to study. And then we need the main magnet, the gradients, and the radio frequency coils, which are the basic hardware components, coupled with the pulse sequence reconstruction methods and image analysis. And today, artificial intelligence is entering the field of magnetic resonance as well. Here are shown some example of commercial equipment that you can buy. This is an MR spectrometer, and those are scanners for imaging with small animals models or human applications. Here is shown a low field scanner with open space useful for open application where the patient can stand in the magnet. This is a more classical scanner where the field can scan from 1.5 up to 10, 12 Tesla for clinical application, as it is currently object of development. My talk will be concentrated on a specific component of the MR hardware, and specifically on radio frequency coils, where the use of metamaterials has been developed in the past 20 years, but especially in the past 10 years. For the one of you that are not used to radio frequency coils, just you can imagine as antenna able to generate RF pulses that are used in the transmit phase of the experiment. And the goal is to provide a spatial distribution of the radio frequency magnetic field in a given location with respect to the body of the patient that we are studying. And in the second part of the experiment, we want to use the same radio frequency coil on another radio frequency coil to detect the induced signal by the nuclear spins in the body. So radio frequency coils are designed with in mind a number of features that depends on the frequency of operation, ultra low field from ultra high field, the nuclei of interest, the spatial targeting of the radio frequency field, safety, since as we will see, there are losses that are induced by the electric field of the radio frequency we are using. And then, of course, as Silvio was saying in the introduction, we aim to achieve the maximum sensitivity for a given application, but also versatility in terms of what we are looking, what part of the body we are looking, or the size of the sample, small animal or human body is also very important in the design itself. To this respect, just to show how it is made a standard RF surface coil, which is shown here, you might find the name like loop gap RF coil or loop gap resonator or split ring resonator. They are all equivalent. As I was saying, the coil is needed to produce a current which is circulating here in this metallic part and needs to be tuned to the alarm frequency of operation. And this is done usually by using some capacitors which are connected to the loop coil. So if we tune the coil properly, we can make this resonant circuit which will provide a magnetic radiofrequency field which is coming out of the plane, like along this direction X in this reference system, and this field will produce the rotation of magnetization by a given flip angle, for example, 90 degrees. This coil is a surface coil. It can be arranged in an array, or we can use this principle to build a volume coil that is surrounding completely the human body, like here in this configuration. But the physical principle is the same. We need to produce in a given spatial location. For example, here, this is the coil. Here is where the sample is located. We need to produce a radiofrequency magnetic field, which will be reasonably located close to the surface of the coil. For example, here is the surface, and this will be more or less the region or volume of interest where we are going to position our sample. This is our aim. And if we design properly the coil, we will try to optimize for a given specific application signal to noise ratio, both in terms of the transmit field and the receive field, with the option that we can use the same coil for both the transmit or receive, or separate coils for the transmit mode and the receive mode. This really will depend on the specific application we are going to use. But when we design a coil, we also need to take into account that the coil, depending on the frequency, will produce a large electric field which will be somehow superimposing to the volume where the sample is located. And this electric field will give some troubles in the experiment, because we'll reduce the signal to noise ratio by additional noise, and might also induce heating in the sample. And this is related to the safety aspects of the experiment. To this regard, there are strict guidelines in the design and use of research or commercial coils, and there is a parameter which is called the specific absorption rate, defined by this equation, where the component of the electric field within the volume of interest need to be calculated and measured, or at least estimated, such that the coil does not increment the temperature of the tissue higher than a specific value that depends on the guidelines. So there are many parameters that need to be taken in account in the design of RF coils. And since the invention of magnetic resonance, or now more than 50, 60 years ago, there have been lots of effort to improve as much as possible the technical field of RF coil. And probably today you have here shown the state of the art of the technology. Here is an example of a clinical scanner. Here, this is the patient, and you can see that here the patient is completely covered with a set of radiofrequency coils that goes from head to toe, and the experiment allows once the patient is inserted in the magnetic field to obtain a full body image covering from head to feet. And this is quite interesting application depending on the anatomy or pathology or physiology that you would like to study for a given patient. There are coils that are specialized for a given dissect, for example, for the eyes only, for ocular application, and here is shown a very high resolution image where you can see fine details of the eye. And this has been used since a number of years, and a current trend is going toward ultra high field application with the aim to get higher spatial resolution, which might be similar with respect to optical images techniques like OCT. Another application that I would like to just to mention briefly is the fact that magnetic resonance imaging is a multimodal method where you can look at the signal of the water protons like it is shown here in these images, but using the same scanner with additional hardware, you can also detect on the same subject the signal from other nuclei like sodium. And this is a very interesting paper which was published a few years ago, where it's showing that the accumulation of sodium is associated with the disability and progression in patients with multiple sclerosis. As you can see, this is the healthy subject, and you have a map of the sodium concentration, which is shown here. And as the degree of disease increases, the images with this along the sodium channel show a significant variation with the scale of disease. You observe also some anatomical changes in the proton images, and you can then put in relation the proton and sodium information to get a wider view of what's going on in the patients over time, because this method can be used in a longitudinal way over time. If we look at the current trend from the point of view of methodological development, I would say that in the past 20 years or so, we have seen a number of significant steps. One was the introducing of parallel imaging, both in transmission and receive mode. Then we have been going towards ultra field applications with a number of large scanners installed in worldwide in Europe as well, with the aim to get higher spatial and spectral resolution. But there is also a trend towards ultra low field imaging. For example, this is a 60 millitesla scanner, which was introduced just a year ago by a commercial company with the idea to bring the scanner to the patient. And there are a number of applications where mobile MRI is going to be applied. Of course, artificial intelligence is more and more used in the field of NMR and MRI. And the aim of my talk today is to show just a few examples where metamaterial science is meeting magnetic resonance. And as you can see, since the introduction of metamaterials in MRI, there has been a growing interest in terms of groups and publication year by year. But why we should look at metamaterial science when we work with NMR and magnetic resonance imaging? Basically, because metamaterials are engineered structure that are designed to interact with electromagnetic radiation in a desired fashion, in a useful fashion. And this is what we do in MRI. We use radio frequency field, both the electric and the magnetic component, to design our specific experiment. So the availability, of metamaterials hardware can be attached to the design of the standard radio frequency coil, such that to better optimize the experiments. And to this respect, I think it's important to understand that when you do metamaterial design, you use what are called meta-atoms, which are engineered structure, and I will show a few examples in a minute, that need to be small size compared to the wavelength of the radiation you are using in your NMR MRI experiment. This is the general approach which has been used in the past 20 years, and it is based on the effective medium approximation, where a large array of meta-atoms, which are made by small size radiofrequency coils for our application, will provide in the spatial volume of interest an effective value of the permittivity and permeability. And the combination of permittivity and permeability, it's what we need to decide in the design stage of our experiment. And if you look at this graph, in terms of choice, we can select basically 4 areas depending on the value of epsilon and mu in terms of absolute value and also of mutual relative sign, positive or negative. When we work with magnetic resonance, what we would like in many experiments, be able to use a metamaterial which allows to get a permeability which is different from one, possibly in some experiment very large, or in other experiment a negative value, so we can work here or here. Or in other experiments, we aim to get an effective permittivity which might be positive or negative with a very large value, for example. All of these are useful application, and what we would like to do is to have these effective parameters with the design values at the radio frequency, and then effective values at very low field in the static limit, where, for example, we wanted to have a magnetic permeability which is 1, such that the metamaterials does not introduce a perturbation to the main static field, so there will be no artifacts in the final experiments. This is what we aim when we design metamaterials. And to this respect, there has been a number of milestones that have been achieved over the year, which are strongly related to the application in magnetic resonance. Just briefly, it's really important to remember that this field started with an important paper by a Russian physicist, Victor Veselago. He passed away a few years ago, and he was a pioneer in this field. Then nothing happened for many years since John Pendry and his group showed that it was possible to produce artificial magnetism with negative value from a number of conductors. And then with this seminal paper and the year after the experimental demonstration really started the introduction of metamaterials in magnetic resonance imaging with the first paper published on negative permeability metamaterial on Science in 2001. And since then, there has been really a large number of groups interested in this application, and I will show just a few examples. How are made metamaterials? It's very simple in terms of design, because we know from the past research on magnetic resonance how to build radiofrequency coils. And here are shown a number of radiofrequency coils, for example, here or here, that we use currently in our application. For example, this is a loop gap resonator, which is basically the surface coil that I have shown before. This is a circular design, this is a square design. So we had already in place the basic elements to build the metamaterial addition to our experiment, but as I was saying before, to make an effective permeability, if we are interested in artificial magnetism, then we need to use a very large array of meta atoms that are small compared to the wavelength. And that's what has been done. This is an array of smaller size loop gap resonators that are arranged either on a plane or in a number of planes, such that the 3 dimension can be covered and a 3-dimensional space will be filled by such small resonators. I talk about resonators because metamaterial technology is a band selective technology. We wanted to get, for example, a negative value of the magnetic permeability at a given frequency, which will be the Larmor frequency of operation. To do this, we need to tune the metamaterial with respect to the Larmor frequency. And this is part of the design which is reported in the technical paper about metamaterials. But what are the main field of application, both in terms of technology and then application of metamaterials in magnetic resonance? And here is shown again the graph before. Here we have what are called double positive group of metamaterials, let's say the standard common dielectric, which are used quite often in our experiments. But today, dielectrics are used as quite often for many applications like dielectric pads, where the epsilon is positive and we aim to get a large value that then needed to be matched to the specific application for radiofrequency shimming. This concept was introduced quite a while ago in magnetic resonance imaging, but only in the past 10 years has been really used with a number of materials that are really making the difference for radiofrequency shimming. Another application of high performance dielectrics is the use of dielectric resonators. This has been already used for electron spin resonance spectroscopy, nuclear magnetic resonance spectroscopy, and today is also used for imaging applications. And there is a large body of knowledge about the use of dielectric resonators, but today some of them are used as in a specific way, just probably to justify the name of metamaterial use of dielectric resonators. On the other side, there are the magnetic negative group of metamaterials. Here we aim to have a magnetic permeability which has a negative value, and possibly when it's needed a large value in terms of absolute number. They are used for a number of applications like radio frequency flux guides, metal surface and RF shield, multinuclei applications, and so on. The main technology is the one I have talked about, the use of a large array of split ring resonators, but today there is also a new trend which is coming from nanophotonics, but we are aiming to use the all dielectric metamaterial design also for magnetic resonance application. And this is the aim of our recent work. Just to show one example where metamaterials were used the radio frequency flux guide at 0.5 Tesla. Here is an assembly of what were called the Swiss roll, which are basically a multi-layer loop coils which develop along this direction. The combination of inductance and capacitance between the multi-layer makes sure that this structure, which is shown here, is tuned to the Larmor frequency at 0.5 Tesla, which was the first application at 21 megahertz. This structure, when is positioned between the anatomy, in this case was the thumb of a volunteer, and a standard radio frequency coil, is able to couple the standard RF coil to the sample, which is located in a remote position. So to this respect is a flux guide and allows the thumb to be positioned far away from the RF coil. And if you do not use the metamaterial, you don't see anything with the standard coil. But if you couple the standard coil with the Swiss roll, then you can see the anatomy at a large distance. This is the image obtained with a full body RF coil. So this was the first application of metamaterials in MRI. There have been many other applications. This is quite interesting. It was introduced by the group of Professor Freire in Spain, and it's working on a principle of magnetic field lenses. Here, the goal was to design a lens which is made again with a large array of small loop gap resonator positioned between the two legs. Here is the standard RF coil, and the goal is, in standard use, you can observe one leg at a time. So you can observe with one coil the first leg here, or you can move the coil here and look the second leg here alone, but because of this large distance, you cannot see both. The idea of the group in Spain was to use a lens positioned between the two legs with a magnetic permeability of -1, which is able to produce a field, a kind of refocusing of the RF field in this leg with some efficiency with respect to the main basic coil. And as you can see here, the presence of the magnetic lens allows to detect with some gain in terms of signal to noise ratio also the second leg. This is an idea which has been developed by other workers using a different design, for example 1.5. Here they have used as a meta device a number of linear elements that are arranged in a given volume, and this is resonating at 1.5 Tesla. This meta device is positioned below one arm, and the standard and the other arm is without the meta device. The subject is inserted in the wool scanner, and the wool body coil is used to scan the subject. As you can see here where there is no meta device, the signal to noise is very low. Here below the other arm, which is this here, the presence of this wire-based meta device increases with a kind of focusing effect the radio frequency field produced by the wool body transmit coil. And this will produce a significant enhancement of the field in this location. This work was done by a collaboration by the group of Professor Belo in Russia and Professor Van den Berg in Holland. There are many other applications based on this design, and just I want to cite the work done by Andrew Webb at the University of Leiden, where following this line of design, they have used a number of zigzag conductors designed to operate at the proton frequency at 7 Tesla and at the phosphorus frequency at 7 Tesla. Combining the design of zigzag elements that are tuned the two frequency, they were able to show the ability of proton and sodium imaging, with the ability also to get in vivo spectroscopy with the phosphorus nuclei, a very important application for metabolism studies. We have been also working our group in collaboration with the group of Professor Monorchio at the University of Pisa to develop double-tuned coils suitable for 7 Tesla ultra field application for sodium, using a spiral design, a number of spirals which are located in between the sodium and proton coils. And we were able to show on the workbench that this design with these meta spiral coils is able to decouple the two channels. Other work is concentrating on another part essential to the working of a radio frequency coil. For example, if we use a bit cage coil, quite often we need to have a radio frequency shield, which is positioned externally to the conductive element tuned to the radio frequency of operation. One problem with the current design is the presence of the shield, which is sometimes quite close to the actual bit cage, reduced the effective field at the central area. And this is due to the presence of mirror current introduced by the conductive layer of the radio frequency shield. A number of groups, including the group in mosque in St. Petersburg and at the University of Utrecht, they are working on the design of artificial magnetic shields that are based on the arrangement of loop gap resonators tuned at the resonance frequency of operation. And they are showing quite interesting improvements, at least in terms of reducing the signal, the specific absorption rate, which is also quite important for applications. Another field of operation is the use of high permittivity materials that are going to find application of radio frequency paths. That means we are positioning high permittivity materials in the volume close to the volume of interest, such that to change the radio frequency distribution within the human body produced by the transmit or receive radio frequency coil. And here is shown the comparison of, for example, of an image obtained without paths positioned here, and you can see the signal here is very low, and it will increase significantly when the paths are located, because these high permittivity materials will perturb significantly, will enhance significantly the radio frequency distribution close to the surface of the paths. This concept has been taken one step further, where instead of using dielectric paths, which are made by a combination of dielectrics, and there is a large literature which is developing, it's instead of using the, let's say, standard dielectric paths, now there is the possibility to design artificial dielectric paths made again by conductors and capacitors which are tuned to the right operating frequency. And it has been shown that the artificial dielectric paths will provide a similar enhancement of the radio frequency field close to the path itself. Those are just some examples where metamaterials are used and find applications. There are applications also in terms of spectroscopy, where, for example, dielectric resonators are used as radio frequency coils when you open a cavity within the volume of the dielectric, which is selected at a specific resonant frequency. And then you insert your test tube inside the volume to obtain the radio frequency field, to use the radio frequency field along this direction, which is needed for the spectroscopy experiment. Working on this line of research, we have been in the past few years exploring the use of metamaterials in magnetic resonance imaging, where we have explored the possibility of excited surface plasmons within our metamaterials. And the technical details are reported in these 3 papers and this recent patent application from our group. Very quickly, in a minute, I just want to show the basic configuration of what we are proposing. This is the standard sample. Might be a test tube or a tissue, whatever. This is the standard radio frequency coil, which is positioned at some distance, usually a very close proximity to the sample. And this is what we have produced in our first design, which is reported in this paper. This was what we call a metamaterial slab, where we have designed the slab to have a negative value of the magnetic permeability, and to have losses which are as small as possible. With this configuration, the presence of the metamaterial slab will introduce a significant enhancement of the radio frequency field within the sample. And if we design in a proper way the metamaterial and the properties and the mutual distance with the standard radio frequency coil, you can observe a significant improvement of the signal to noise ratio within the sample at few centimeters along this direction. The enhancement will depend on the magnetic permeability that we can achieve at the Larmor frequency of 1.5 Tesla, but also on the losses, the additional losses that are introduced by the metamaterial. And if we are able to design a metamaterial with very small losses, then the enhancement can reach quite large values. Based on this design, we have been exploring other geometries instead of a slab, a spherical geometry, and we have reported quite recently in our paper and the patent that the spherical geometry allows to have a number of modes that will present a negative permeability. And we are able to select the resonant modes of this magnetic permeability sphere, like in the modes of a dielectric sphere, and the modes are reported here. Depending on the mode, we are able to obtain relative signal to noise ratio to the condition without the metamaterial sphere that can reach a level up to 6 times the signal to noise ratio. This seems quite an interesting enhancement. Of course, all of this is related to the losses, and we are studying way to make such a sphere with the loop gap resonance technology, such to have very small losses. But the other direction that we are exploring, and I will talk about this in the last 2 minutes of my talk, is to move from a spherical metamaterial with a negative magnetic permeability to a spherical dielectric resonator sphere having the same sides, but with a electric permittivity that is designed such that to mimic the magnetic permittivity. So the idea is we want to have a negative magnetic permittivity, for example, of around -2, which will give here one of these peak, which will provide an enhancement within the sample. But instead of using the magnetic metamaterial sphere, because of easier technologies, we mimic this condition with a dielectric resonator that can be constructed much easier. And with the current technology, it's possible to achieve a larger value of the electric permittivity. And in our recent papers, we have shown that theoretical framework. What we have reported from full wave simulation is that if we start with this field distribution and signal to noise ratio distribution with the standard RF coil, and we add here the dielectric sphere, we can observe along the main axis, which is this here, the Z axis, a significant improvement of the transmit-receive radio frequency field down to few centimeters. And if you compare the V1 field amplitude, this will translate from our simulation in a large sensitivity enhancement. What we have moved, basically, what we have done is basically to move the radio frequency field towards the central part of the sample by means of a dielectric. But our idea is to make the dielectric a dielectric resonator so that it will have a large quality factor with the possibility to improve the V1 field proportionally. The other improvement which seems quite interesting is that the presence of the dielectric resonator moves also the electric field within the dielectric resonator to some extent, not in a full way, but to some extent. And this means that our calculation shows that the specific absorption rate within the sample with the presence of the dielectric resonator here within the sample will be reduced by around 40%, which seems quite interesting. Our model allows us to select the resonant mode of the magnetic permeability or electric permittivity, and each mode will produce a magnetic and electric field inside the dielectric resonator and outside that can be selected for the specific application in terms of magnetic or electric field. And this gives us a large versatility. We are moving from the theory to the experiments. We were able to purchase dielectric resonator spheres from IQ research company in the United States. They designed the sphere on our specifications, and just recently we were able to measure the dielectric resonant mode of a sphere of 4 centimeter diameter, and those are the experimental modes for a sphere with epsilon 170 and a sphere epsilon 3000. We are aiming to use this sphere with this mode for 3 Tesla applications, and we are very close to the useful resonant frequencies that we have been to design. So I hope quite soon we will be able to add an image in this configuration, hopefully where we are able to show improvement of signal to noise ratio and improvement of a specific absorption rate. In conclusion, our specific results at 3 Tesla shows the potential for improving MRI at 3 Tesla, and we believe also at higher field. Of course, the losses in the metamaterial is an issue, and there is a lot of research in the field of metamaterials and metamaterials applied to magnetic resonance to decrease those extra losses. We believe that metamaterials need to be carefully considered in a number of experiments for spectroscopy and imaging, and possibly the design step needed to be optimized depending on the specific application. We, as an Italian group, but as you have seen, there are a number of groups in Europe that are working on this subject. We will be very happy to collaborate with our colleagues and with you, and we are very happy.